Welcome to the Tech Study channel. So in the previous class we have discussed about the ninth question and its answer. So now we will discuss 10th question and in its half answer only. Okay. So this video is 8th video, part 3, because in the part 1 we have discussed about BJT act as a switch and amplifier, which is one type of transistor, and in the second part of 8th video we have seen FET. In FET we have seen JFET act as a switch and amplifier, and now in this video we will see MOSFET. In MOSFET, DMOSFET, N-channel DMOSFET act as a switch and amplifier. So this topic, N-channel DMOSFET act as a switch and amplifier, is included in the construction and working of MOSFET. Okay, so I'm explaining its answer now. Okay, so first we will see what is transistor. Transistor means a fundamental semiconductor device used to switch or amplify electronic signals and power. Switching means switching on or switching off, and amplifying means increasing the strength of the signal. Okay, and then transistors are categorized by whether they are controlled by input current or input voltage. If they are controlled by input current, then they are called current control device. Example, BJT, bipolar junction transistor. And if they are controlled by input voltage, then they are called voltage control device, FET, field effect. Example, field effect transistor. So next we will see what is FET. So in this class what we will discuss means what is transistor and what is FET and what is MOSFET and types of MOSFET and EMOSFET working and construction, plus 3 regions of EMOSFET and their graphs also in each region. Okay, so this DMOSFET and working and construction plus 3 regions of this is DMOSFET. We will discuss in next class. So what is FET? So FET is a voltage control 3-terminal semiconductor device used for switching or amplification. Okay, and so this MOSFET is one type of FET. Okay, then we will see what is MOSFET. This is full form is metal oxide. One second. So metal oxide semiconductor field effect transistor. So it acts like a electric wall where a small voltage applied to gate terminal. By applying it, we create a electric field which opens or closes the channel for current to flow between source to drain. So we understand this statement by using EMOSFET diagram. So here is the EMOSFET diagram. This is the initial diagram and this is the final diagram after channel is created. So here it is saying a small voltage applied to the gate terminal. Here is the gate terminal. Okay, 3 terminals are there: source, gate and drain. We create an electric field which opens or closes the channel for current to flow between source to drain. So this voltage, gate voltage, this small gate voltage creates an electric field which opens or closes this conducting channel between two regions. There is a conducting channel for the flow of electrons. So this electric field opens or closes the conducting channel for current to flow, okay, from source to drain. So then we will see it is a active device who can control flow of electrons, okay, using external voltage source. So then BJT, examples are BJT and JFET. MOSFET is of two types, D MOSFET and E MOSFET, and they are further divided into N channel and P channel. N channel D MOSFET and P channel D MOSFET, and N channel E MOSFET and P channel E MOSFET. So what is E MOSFET? E MOSFET is a normally off electric switch. Normally off means there is no channel between N and N, so there is no current flow between source and drain. And it creates one channel where one didn't exist. So here it created a channel where the electron flows. Then we will see construction of it. The gate is not directly connected to substrate. Here is the gate. So this is the N channel E MOSFET diagram, okay. MOSFET diagram. Here gate is made up of metal or polysilicon, okay. And source and drain are N type materials, and here is the P substrate, okay. Here also a metal. Here is the ohmic contact will be there. So what is ohmic contact I will explain later. Then we are here. So the gate is not directly connected to substrate. Here the gate is there, and here silicon dioxide layer is there, and then this is entire thing is P substrate. So here they are saying gate is not directly connected to the P substrate, and it is located over silicon dioxide. Here is the silicon dioxide, okay. And then it is width is 100 angstroms, and width means this width. There is no channel. It is indicated by dotted lines. It is the circuit representation of E MOSFET. It is P channel and N channel. Two types of E MOSFETs are there. So there is no channel. So that's why it is initially there is no channel. That's why it is indicated by arrow dotted lines. Okay. The arrow mark indicates flow of current. B means substrate, D means drain, G means gate, and S means source. Okay. Then two heavily doped N plus regions are placed in lightly doped P-type silicon substrate. One N plus region is called source and other is drain. They are separated by 1 millimeter distance. Okay, these are the two N plus regions, which is placed in lightly doped P substrate. Okay, and one N type region is called source and one another is called drain. And silicon dioxide is a insulating layer, means is a insulator and of width 1000 angstrom, and also called the gate oxide also. And consider two plates. One plate is of metal contact of gate. Here is the gate. Okay, so here the gate and silicon dioxide and the P substrate is considered as a parallel plate capacitor structure. So Y means gate is act as a positive plate and substrate is act as a negative plate, and in between silicon dioxide is act as a dielectric. Okay, so the considering two plates, one plate is metal contact of gate, and other is substrate, and between them a silicon dioxide layer is placed and act as a dielectric. This combination is called parallel plate capacitor structure. Here we can observe gate, silicon dioxide and substrate. Okay, here is the VGS voltage, ID current will be here. Okay, from current direction, drain current, and VDS voltage is here. Here the VGS and VDS are both are positive. Okay, so in the first diagram the channel is not formed. We didn't apply any voltage here, VGS voltage. So after applying, the channel is created. So in the working we will see how the channel is created. Here the gate is act as a positive plate. And substrate as a negative plate. Here is the substrate which is just below the dioxide layer, and means silicon dioxide layer, and silicon dioxide act as a dielectric, means insulator, where the silicon dioxide prevents current from flowing directly from the gate to substrate. So as we all know, the current flows from positive terminal to negative terminal, or positive plate to negative plate. So this silicon dioxide, which is an insulator, that is preventing current from flowing directly from the gate to substrate, allowing electric field to build up instead. So in the working we will see how the conducting channel is developed. So before that we will see why the N regions are heavily doped and P-type substrate is lightly doped. So why the N plus regions and P substrates are heavily doped and lightly doped respectively means, so N type regions heavily doped because it act as a reservoirs of charge carriers, electrons. Okay, because heavily doping means adding more amount of extra electrons to the N type regions. So it act as a reservoir of charge carriers means electrons. Heavy doping ensures there are plenty of electrons available to be injected into the channel once it is formed. Okay, and then the N plus regions are heavily doped because high doping ensures low resistance means ohmic connection between the metal terminals, source or drain, and the semiconductor P substrate. So to understand this statement, we have to understand what is ohmic connection or ohmic contact. So ohmic contact means it provides a linear low resistive electrical connection between the metal and semiconductor. Semiconductor means p-type substrate over the operating voltage range without significant rectification means without converting AC to DC. See, so where these ohmic contacts are present means in the these are the ohmic contacts. The dark lines indicates ohmic contacts. Okay, this and this, source and drain. Okay, and this p-type substrate also have ohmic contact just below it, and which is provides a linear low resistive electrical connection between the metal and semiconductor. Semiconductor means P substrate over the operating voltage range. Okay, so metal is the ohmic contact means the source and drain terminals. So ohmic contacts are made up of metals means source and drain are made up of metals. So how it provides low resistive path for electrical conduction. Electrical conduction means flow of electrons. Okay, this is actually a flow of electrons between N-type region and a P-type substrate. Because we have weld N regions into the P substrate, so there should be electron flow from the N-type regions to P substrate so that the conducting channel will form. So that's why ohmic contacts are helpful to flow of electrons, which creates low resistive path. Okay, so how they are helpful means when metal touches a semiconductor, a potential barrier means ohmic contact metals touches a semiconductor means p-type p substrate, a potential energy barrier forms in a lightly doped semiconductor. This barrier is thick. So in the diagram, this is the ohmic contacts and this is the P substrate. they are uh, the end regions are welded in the p-type substrate. So the potential energy barrier forms. Here the potential barrier potential energy barrier will form, okay, here and here, okay. In a lightly doped semiconductor, means p-type substrate, this barrier is thick. Electrons must have enough thermal energy to jump over the barrier to move from the metal to the semiconductor, means from n region to p substrate, okay. And for conduction of channel between two n plus regions. So that's why n plus regions are heavily doped, so that this barrier becomes thin, because the width of the barrier or depletion layer is inversely proportional to the doping concentration, okay. Then we will see why is p substrate lightly doped. If the substrates were heavily doped, the gate would need a much higher positive voltage to push away the many holes and pull in electrons to form the n channel. Here it is saying, if the substrate is heavily doped, means extra holes are more amount of extra holes are added to it, then this gate voltage, we have already seen, we apply a small voltage in the MOSFET definition to control the open or closing of a channel. So p substrate is, if it is heavily doped, then the holes of it, to push the holes of it and to pull the electrons of it, minority carriers of it, the gate voltage should be more. We need more gate voltage. So that's why the p substrate is lightly doped. Light doping keeps the operating voltage at a practical level. And then we will see working of EMOSFET. So gate is of p-type material. It is not p-type material. It is a metal or polysilicon, okay. It is heavily doped because to provide high conductivity, means perfect conductor. It acts like a perfect conductor by functioning effectively to quickly transmit voltage signals. Heavily doping increases the charge carrier concentration, making the material conductive. The narrowing and the second reason is why it is heavily doped, means to narrowing the depletion width. When metal wire meets a semiconductor, here the semiconductor is gate, okay. So to narrowing the depletion width, when metal wire meets a semiconductor, means gate, a potential barrier naturally forms. So here is the gate terminal, here is the metal wire, okay. Metal wire is there. Between these two, a potential barrier is formed. By heavily doping the gate material, the depletion region at this interface becomes extremely thin. As I said, because the depletion region is inversely proportional to the doping concentration. That's why the depletion layer becomes thin. The gate is heavily doped because the silicon dioxide layer is an insulator. It prevents electrons from moving physically from the gate into the substrate, leading to very high input impedance. So this is not because of heavily doping. These these are two only reasons why it is heavily doped. So in the working we are seeing it. So working of the EMOSFET, the third point is because the silicon dioxide layer is an insulator. It prevents electrons from moving physically from the gate into the substrate, leading to very high input impedance. So this is the silicon dioxide which prevents the what it prevents electrons from moving gate terminal to substrate. Okay, here is the substrate. This is the insulating material. Gate, this insulating material means silicon dioxide prevents the electrons from gate terminal to reach the substrate material. Okay, so then since charge cannot flow through the oxide, a positive voltage applied to the gate VGS causes a positive charge to build up on the gate side of the capacitor. So here it is saying that charge can't flow through the oxide, means silicon dioxide. A positive voltage applied to the gate VGS causes a positive charge to build up on the gate side of the capacitor. So here it develops the positive charge. Okay, here we are applying VGS, positive voltage, to flow the carriers from gate to substrate. Okay, so here and negative voltage applied to the substrate. The negative voltage is given to the substrate. Okay, so the positive charge built on the gate creates an electric field that penetrates through the oxide into the substrate. Okay, this voltage which we have applied as VGS is creating a electric field which is penetrates into the silicon dioxide layer. This field performs two tasks. It repels the majority carriers holes away from the surface. So B.tech material has majority carriers of holes. So this repels, this electric field repels the holes Okay, holes of the p substrate, and then it attracts minority carriers electrons from the bulk of the p substrate towards the oxide interface layer just beneath the silicon dioxide, and it is also attracts electrons from n plus regions, and this electric field attracts the electrons of the p substrate, which are the minority carriers, and attracts the electrons of the 2n plus regions also. Okay, so here the electrons are accumulated. Okay, so the negative voltage at the substrate terminal repels the minority electrons upward towards the oxide interface. So from here also we have applied negative voltage. So electrons of the p substrate, which are the minority carriers of the p substrates, are repelled by this voltage and flows towards the gate. Okay, and then once the gate voltage reaches a certain threshold, enough electrons once the gate voltage reaches a certain threshold, enough electrons accumulates at the surface to form a thin conductive n-type layer that allows to flow the current between the source and drain. So here we have the electrons are accumulated. So here it creates an conducting channel which allows the current to flow these from drain to source. Between two n channels the current flows. Then there is no current flowing through the gate into the substrate because the silicon dioxide layer act as an insulator. Only an electric field is established here. Okay, so there is no current flowing between gate and substrate. Okay, because this insulator is there in between. See, so it only establish an electric field which creates a conducting channel by attracting electrons. Okay, then the current flows through the wires connecting the drain and source to external battery. The current flows through so drain and source wires. Okay, then we will see three regions of MOSFET. Here first is cut off region. In this region the MOSFET is off. No conducting channel is formed between the source and drain. It is like this. It is like this. No conducting channel will be generated. Okay, why? Because these conditions, VGS is less than VTH, which is medium positive or moderate positive, and VDS is high positive, and ID is 0. So device act as a open switch or off switch. So here VTH is threshold voltage, is the minimum gate voltage required to form a conducting channel. Okay, around 1 volt or 2 volts. Then we will see one example. VTH is 2 volts, then VGS is 1 volt, and VDS is 5, and ID is 0. So we have to see these values are satisfying these conditions or not. So VGS is less than VTH, 1 is less than 2, that is true, and VDS is high positive, 5. Okay, then ID is 0, ID is 0. Then the graph is between ID current, drain current, and drain to source voltage. This is the lowest line at the x-axis. It indicates the cutoff region because there is no current, okay, which is developed. It is zero only. So as this means this graph shows that if we increase id or vds also, the id is independent of vds, so that's why we didn't get any current. Only the line is along with the x-axis only, okay. Then a linear or active region. In this, the EMOSFET is act as a on switch. The MOSFET is on and a channel has formed, okay. In this region, the drain current increases proportionally with the drain to source voltage. So here is the drain current. It increases proportionally with the drain to source voltage, okay, this voltage. So condition is VGS is greater than VTH, means the minimum gate voltage required to form a conducting channel. And then if we increase VDS, then the ID current also increases, okay. And VDS is less than VGS minus VTH. This is the condition. And ID is moderate. It depends on VGS and VDS, okay. The device acts as a voltage control resistor because the current is varying according to the voltage, so it is called as voltage control resistor. And here id is medium positive and vgs is high positive and vds is low positive. So example is vth is 2 volts, then vgs 5 volts and vds is equals to 1 volt, and the id is 2 microamperes. Here we have to see these values are satisfying the condition or not. So VGS high positive, okay, VGS high positive and VDS low positive 1 volt, okay, and it should be VDS is less than VGS minus VTH. Here is the VDS 1 is less than VGS minus VTH, 5 minus 2 that is 3, 1 is less than 3 that is true, okay. The device is in the linear region. ID might measure around 2 microamperes. So this is the graph between drain current and VDS. It increases linearly with the current, okay. Then saturation region. In the saturation region, the EMOSFET is act as an amplifier. So how we will see now, the MOSFET is fully on. As VDS increases, the channel pinch off near the drain. As this VDS increases, the channel pinches off near the drain. Because pinch off means meeting up of two depletion layers or two layers, meeting up of two layers. So because the drain is of n-type material and the p substrate is of p-type, okay, this is n-type, drain is n-type and p substrate is of p-type, so the reverse bias occurs. We are increasing the VDS, so the reverse biasing occurs between these two, and the depletion layer of drain coincides with the channel near it. So here we already know that there will be thin depletion layer will be there because This is N type and this is P type. Due to because of two different types of materials, the reverse biasing occurs, and hence the depletion layers are formed. So how these depletion layers are formed means uh, n type materials have what the positive donors, and the p type materials has negative acceptors. So these positive donors and negative acceptors are recombined with each other. So the depletion layer will be formed here and here. Very thin it will be. So the depletion here, it is saying that so now the drain terminal, which is n type region, is increased, means VDS is more increased, more positive. So here the depletion region increases. Okay. And coincides with the channel near it. Here is the channel and it increases and coincide with the channel. So current saturates, means becomes constant. Okay. See, so the amount of electrons going into this n type region is constant. So the condition is VGS greater than VDH and VDS greater than or equals to VGS minus VDH. So VDS, VGS and ID should be high positive. And drain current. Drain is high and stable. It is now controlled by VGS. VGS voltage, gate to source, gate to substrate voltage, and is nearly independent of VDS. Because here the electrons are provided by gate terminal only due to this VGS voltage only. So as we increase VDS, here it is saying controlled by VGS. Here the ID current is controlled by VGS, not by VDS. So if we increase and increase VDS, the ID becomes independent of VDS. Why means the electrons are provided by gate terminal only. Means which means VGS only. Indirectly through the VGS. So we are increasing voltage, but the number of electrons that will accumulate in this region will be decided by the VGS only. So uh, this current will become independent of VDS. If we increase VDS more and more, and if there is a sufficient number of a constant number of electrons are there, a constant number of electrons are coming due to VGS, so a constant current will be generated. Okay. So it becomes independent of VDS. That means we are increasing the pressure of the electrons, but not the number of electrons. So number of electrons is decided by VGS only. Though, so the ID current is also decided by the VGS only. Okay. Then the device acts like a voltage controlled current source. So here we are controlling current by using voltage. So it is called as voltage controlled current source. Then example is VDH is 2 volts and VGS is 5 volts and VDS is 10 volts. So these three should be high positive. As I said, condition VDS, VGS and ID. VGS, VDS and ID both are high only, 5, 10 and 5 microamperes. And the condition is VDS greater than or equals to VGS minus VDH. Here is the VDS 10 greater than or equals to 5 minus 2, that is 3. 10 greater than or equals to 3, that is 2. The device is in saturation. ID might measure STD 5 microamperes. So first it increases, ID increases with the VDS and then becomes constant because of the pinch off of the layers. Okay. And so how it acts as an amplifier means small changes in the gate to substrate voltage leads to significant changes in the drain current, ID. So as I said now, the ID is independent of VDS and it is controlled by VGS. So small changes in the gate to substrate voltage leads to significant change in the drain current, ID, which is the fundamental requirement for amplification. So it acts as a amplifier. Hope you understand the EMOSFET 3 regions construction and working also. So that's it for today's class. If you feel this video is helpful, then subscribe, like, share and comment. And I will see you in the next class. Thank you. Bye.